Hello. Yes. Hello, everyone. This is Professor Pankaj Biswas. I am now in live session. If you have any queries, you can ask me questions. Actually, I am now live for the course that is fundamental of thermo-mechanical analysis and fundamental of what it's called fatigue analysis of welded structure. So if you have any queries, you can ask me questions. I have not yet got any questions. So if you have any questions, you can ask me questions. In last lecture, I was decided to discuss about the what it's called how to do finite element thermomechanical analysis using some standard software packages to simulate the thermal history and what it's called welding residual stress estimation by using what it's called by using some finite element packages like ANSYS, Abacus. So I was discussing that I will explain in today's lecture or today's live session that I am going to present now, because as there is no means live questions, that's why I'm going to present that things as per your requirement. So I am going to share that PPT. I'm sharing these things. I'm sharing the things that will be better. So after that, I'll just discuss about how to do thermomechanical analysis using commercially available software package like ANSYS. So I'm going to present that things. I think this is now visible. 1 minute. Let's see whether it is visible or not. It's visible. Okay, okay, fine. Now I'm going to share this thing. So now in today's live session, I will present this what it's called. Yes. So you see, so I have already told you these things, what it's called, how to do thermomechanical analysis related things. For that, generally, this is the flow chart we need to follow. That I'm going to just sharing the things in full screen. That will be better for you. So you can observe that in this flow chart, there are two parts. In left side part, you can see, just I am just discussing, it will be better to use a what it's called is a whiteboard. That will be better. So you can observe here I am sharing this PPT. In this left side of this flow chart, you observe that is related to thermal analysis. So how to do thermal analysis? For doing thermal analysis, what are the things required? That things I am showing. And in right side part, I am showing a structural analysis detail. So in thermal analysis, for finite element analysis, these are the following information required. You can see. That means, first of all, I have already discussed these things. We need to have some distributed heat source. Then for doing thermal analysis, it is better to use what it's called, temperature dependent material property. Then what material property is required, that I have already explained. Then we need to specify the boundary condition. Then we need to also specify the initial condition. After that, generally, we need to do thermomechanical analysis. In second, you can say column, I have shown that you can observe. There, generally, we need to apply the heat source load based on either volumetric heat source or based on what it's called different types of heat source model, which I have shown in my what it's called lecture, initial first 4-week lecture. There I have discussed different types of derivation part of different types of heat source model. Based on as your requirement, you can decide which heat source you should use. That heat source model we need to use there. After that, okay, we need to just predict the transient thermal history. That thermal history, generally, we need to use as a what it's called a structural load, where generally we can predict what it's called a structural results, that you can say that a structural analysis generally we use here for doing welding to predict the residual stress and well-induced distortion. So for getting the well-induced residual stress and distortion, this transient thermal history result is required first. After that only we can, using that thermal history result, we can predict the what it's called well-induced residual stress and distortion. So how to do these things, that related thing in details now I am going to discuss one by one. So for doing thermomechanical analysis using commercially available software package ANSYS, what it's we need to first choose some what it's called thermal elements, because for doing finite element analysis, you know, we need to discretize the model into finite number of what it's called elements. Let us consider this is a welding plate. Little bit I'm just showing, then it will be more clear to you. So you know very well all these things because finite element related things where we need to first discretize. Discretize means we need to divide this plate into number of small element. So I am just little bit showing. So generally, this one division of this, what it's called, different discretization part is called generally a element. So here let this a small number of what it's called division is its shape is cubic in nature, that you can observe. Now this is a small division, its cubic types of division is called a element. Now with this corner point of this, you know these things, corner point of this element is called node. Now in software packages, generally where generally we need to incorporate the basic fundamental in a particular location to do thermal analysis or structural analysis. Like for tangent thermal analysis purpose, we need to do all the, you can say, thermal analysis related coding. Generally, we need to allocate in a particular location. That allocated location for doing tangent thermal analysis using three-dimensional case in finite element model, generally here it's given a name that is called, here I am just showing solid, you can see solid 70 thermal element. What does it mean? That means in this solid 70 thermal element, here generally all the thermal analysis related, you can say, program is stored. So once you just do the use the software packages, if we select this element, then what happens? We can all the, you can say, data required to do thermal analysis, that related all information generally we can get once you choose this element. So it is observed that for doing thermal analysis, solid 70 model is appropriate, or solid 70 thermal element is appropriate. And for doing structural analysis, which is compatible with solid 70, you can say thermal element, that is called either solid 45, earlier it was solid 45 elements, and now it is known as solid 185 element. So using this solid 185 element, generally what happens? We can do the structural response due to thermal loading. Thermal loading means due to moving heat source or welding heat source analysis. Welding analysis using moving heat source, whatever the thermal result will get, depending upon that things, whatever the structural change occur in the model, that related things we can predict. This you should keep it in mind. So in solid 185, generally all the you can say programming related to a structural response is stored. That's why once we'll choose this solid 185 element for structural analysis, then we can get the thermal response on a structural model, how it is, that related things we can get. So I have already written for doing this thermo-mechanical analysis, what we use a volumetric moving heat source. So volumetric moving heat source generally I have already discussed. So that volumetric moving heat source can be double ellipsoidal heat source model, can be semi-ellipsoidal, can be conical, depending upon the requirement or depending upon the type of welding process, which heat source model is appropriate for which welding process, that I have already explained in my lecture. So we need to choose that what is called heat source model. Okay, after that, these are the generally thermal analysis related governing equation. So based on this governing equation, I have already told you, based on this governing equation, we can decide, based on this governing equation, we can decide, you can say, what should be the input parameter to require the thermal analysis. So this governing equation here is showing, which is called Fourier transient heat conduction equation. So from this equation itself, I have already discussed in detail. Here the output is temperature T And for getting this temperature T, in this equation, from this governing equation itself, you can get the idea what are the input required. So here the input required are K is called thermal conductivity. You can see rho is called density, C is called a specific heat, and X, Y, Z are the coordinate. X, Y, Z are the coordinates. So from this governing equation itself, you can get the idea. To get the output T, what are the input required? So this input generally we will use in this what it's called analysis. That is called that is generally temperature dependent. That means it is not a constant material property. If you use constant material property, then what happens? You will get the result, but that result will not be very accurate one. So that's why it is better if you will use what is called temperature dependent material property, that is thermal conductivity, density, specific heat, then what happens? You will get more appropriate result. After that, we need to specify the boundary condition for doing this thermal what is called analysis. So first of all, we need to specify the initial boundary condition. Initial boundary condition means, as it is a transient analysis, so transient analysis means where the load is varying with time. This you should keep it in mind. Because in case of welding, you observe that there is a heating cycle as well as there is a cooling cycle. That means with time, the temperature curve is coming, you know, these things. That is, this is your temperature, this is your time. So with time, generally, this temperature is varying. It is not constant. So if in a analysis, the load is not varying with time, that is called a static analysis. If in an analysis, if the load is varying with time, that is called transient analysis. So as here it is varying with time, that's why what happens here, we need to use at time t equal to 0. That means when the time is, that means welding heat source not yet start moving, then what should be the condition of the plate? Plate means, let us consider this is your this one plate, this is your another plate, two plate. So this two plate we are going to weld together at this middle zone, you can see. For doing these things, we need to first specify what is the initial condition of this plate surface or plate. So here generally initial condition we need to define considering time t equal to 0. What is the condition of this plate? So here when time t equal to 0, all the plate surface temperature is atmospheric temperature. Atmospheric temperature here, depending upon your season, we can decide, let us consider, we can decide a atmospheric temperature, let us consider 25 degrees centigrade. So this we need to specify over the entire plate before starting the moving heat source. After that, we need to specify the other boundary condition. That other boundary condition is, one is called, you can see, is called convection boundary condition. Another one is called radiation boundary condition. Apart from this thing, this by this generally first boundary condition here I am showing. Here generally we are applying heat source model. So how to do all this thing using commercially available software package, that I am going to show you. So here you can see generally, let us consider this is a well bit geometry. So based on this well bit geometry, we need to do the modeling part. Here you can observe generally this well bit geometry cross section we have got from the experimental observation itself. So based on this well bit geometry, here you can see we need to generate the well bit in the weld zone, which I have shown in this right side figure, you can see. So here you can observe that this well bit geometry which we have developed here, this is a what it's called V-shaped well bit geometry, almost V-shaped well bit geometry that we have already modeled in this finite element modeling part. And left side you see we have modeled the what it's called the left side plate, and right side we have modeled the right side plate. And we have also modeled the what it's called bit geometry for doing the welding operation. Because if we'll consider the bit geometry in our analysis, then it will give us more appropriate result. That's why what happens, we have already during modeling part, we have considered this bit geometry part. Okay. Now, for applying the, you can say, temperature dependent material property, here I have shown with temperature, let us consider like 0 degree to around 2000 degrees centigrade temperature, how the density is varying, yield stress is varying, ion modulus is varying, then Poisson's ratio is varying. So all the different temperature dependent material property which I have taken from some published literature. By using these things, actually, we will show you, or I will show you how to do the what is called thermal analysis as well as structural analysis to get temperature distribution, residual stress, and distortion. That I am going to show. So this is the other temperature dependent material property like a specific heat, thermal conductivity, coefficient of thermal expansion coefficient. So this related temperature dependent material property, you can observe that there is a huge variation with temperature of all this material property. That's why during thermal analysis or structural analysis, if we will not consider this temperature dependent material property, then our what is called outcome will not be very appropriate. That's why it is better to use for doing transient thermomechanical analysis this temperature dependent material property. Just here I am showing just how the moving heat source generally is looks like what happens here. The welding start from this initial position here, and it moves to this direction. Okay. So with the moving of heat source, you see how the heat source is generally, you can observe how the heat source is generally moving and how the heat is conducting over this left side plate and right side plate that I am just showing. Okay. After that, generally, I am showing some example of transient thermal history result that you can observe, because I will show you now step by step. And why I am showing this thing? To show you by using this what is called method, whatever the thermal history or structural result you can get, that result is very well matched with experimental result. Like this is the outcome of temperature distribution versus time. For different location of the plate. Different location of the plate means what happens? Let us consider this is the plate. This is the center line. So at center line, what is the temperature that is generally represent this first curve? So their center. From the center, generally, if we go from the center line, how the different temperature distribution we get at a particular location, that related generally things I have generally presented here. So you observe that once we go from center line to away from the center line, the temperature is peak temperature at center line is around 300 degrees centigrade. It's away from, you can say 5 millimeter away from the well line. Its temperature is around what is called 1000 degrees centigrade. Like this, actually, for different distance, how the temperature distribution is coming, peak temperature is coming, that related information you can get from this result. Now, to validate this temperature result, generally what we did, we generally, during experiment times, we generally inserted what is called, we inserted just I am showing in the second figure, you can see, a thermocouple at a distance of around millimeter from the well center line. So this black color curve, whatever the black color curve I am showing, this is generally represent your experimental data, and this is generally represent your numerical how the temperature is varying at that distance. That means this is the welding specimen. So this is the well center line. This is the well center line. From this well center line at a distance of, let us consider 30 millimeter, by using what is called also. Now I am going to discuss how to predict this what is called thermal residual stress That now I'm going to discuss. So like what happens after getting this thermal history result, once we go for, you can see here, the second figure itself I have shown. In this figure, you can observe that this is the residual exposure. This is the central line of the well. This is from the central line, perpendicular to the well line to from the well central line, and from the well central line. That data also you can get from this simulation. So you can observe from this figure itself that means general in nature, and from the central line, it is complex in nature. So these are the things we predicted from this finite package by using thermo-mechanical analysis. So how to start these things, the related thing I am going to discuss. So for doing mechanical analysis, generally here we use that you can see, and we use ANSYS multiphysics. Just it will be better, little bit big the way I'm showing. This is this is actually, you can see you can see here, this is generally ANSYS multiphysics software. Generally ANSYS software we use. So ANSYS software is based on what? ANSYS software is based on what is called finite element method that you know very well. So in this ANSYS software, generally we can do this welding thermomechanical analysis. How to do this thing, that I am just going to show. Just I am showing an example. Like what happens here, you can see. That means if we do the what is called thermomechanical analysis, then how the tangent moving heat source is coming, just once I will show, then it will be very clear to you. Let us consider this is the temperature distribution moving heat source model by using moving heat source model. Just once I am just showing, then it will be very clear to you. So here you can observe that how the heat source model, this red color one is heat source model, and how it is moving from during welding, and how the temperature is distributing over the entire plate. That things you can observe from this figure. This is for single pass welding I am showing. And we did also these types of modeling for multi-pass welding also. That multi-pass welding related simulation also I am showing. Then that will be very interesting to you. Like here I am just showing. You can see this is, let us consider this fast pass welding. So here you see we are mimicking the weld deposition part also. So first pass welding, then this is our second pass welding. Okay, how the heat source is moving and how the material is depositing, that things also you can observe from this figure. This is left side, the multi-pass welding we are doing. Initially bottom pass, after that another pass. You see different pass here I am showing. And how the temperature and moving heat source is there, that related things also you can observe from here. Just a simple example I am showing. But these types of analysis takes huge time actually. That's why what happens, depending upon our number of pass, generally this time requirement is varying, or depending upon the, you can say, number of element or number of you can say node, generally this you know this thing, that means this computational time is varying. Now I am going to just discuss how to do all this analysis part. So you see, generally here I am showing by using ANSYS software how to do this thermomechanical analysis. What is the full form of ANSYS? The full form of ANSYS is this AN represent analysis, and sys represent system. Okay. You see, so this ANSYS generally once we install in our computer, then this ANSYS icon is appear. You can observe this. Here I am showing this ANSYS icon. You see that you can see this ANSYS icon will come there. So in this ANSYS icons on we double click it, then generally a window will appear, which is looks like this that you can see. Just I am showing these things. So now here generally we need to choose generally what should be our working directory, what should be our type of analysis. That are the things generally we can configure here. So here you can see generally this ANSYS here generally in multiphysics, ANSYS multiphysics, we can do different types of physics analysis. Like here by using ANSYS multiphysics, we can do at a time what is called thermal analysis, then structural analysis, then vibration analysis, then what is called magnetic analysis, then different things we can do. Whatever then electrical analysis. So different things we can do using ANSYS multiphysics. That's why we choose here the license version is ANSYS multiphysics. So you see after that we need to once we after selecting these things, we need to now select our working directory. What should be our working directory? What is working directory? Working directory means here you see where the data will be stored. That we need to specify. For this in working directory, we need to write generally what it's called. Here we can use this DOS form. By using that, we can write our location. Like here I have chosen C folder, document and setting Pankaj. Okay. And here we are doing, let us consider structural thermo-mechanical analysis. So that related thing just here I am showing. That we need to specify. Okay. So in this location, that means whatever the Pankaj file is there, in this file generally all the data will be stored. This you should keep it in mind. So this we need to specify beforehand. After that, generally what we need to do, you see, so here we choose this structural welding analysis. You can see working directory I have written here. You can see welding simulation. And here there are generally job name I have written, that is your welding analysis. Okay. Now we will just show you once you just click OK, you can say that OK means this run button, then we will enter the actual what is called window of this ANSYS software. So in this ANSYS software, you can observe that there are 5 important steps which is required to do what is called any types of analysis. First of all, first one is called preferences. Second one is called preprocessor. Third one is called solution. So these 3 processes required to get the solution, and to get the data from this solution result, we need to use this last 2. You can say what's called menu. One is called general postprocessor. By general postprocessor, we can get the data that is generally you can say that is related to what it's called means contour plot related thing. And by time history postprocessor data, we can get a real data at any node location or any specified location. What should be the stress magnitude? What should be the thermal history magnitude? What should be the temperature distribution varying with time? That related thing, whatever the data we want, that related thing generally we can get with the help of this time history postprocessor menu. That you can that I'll show you one by one. Okay. So in preprocessor, what are the things generally we can do using this preprocessor? That also I am showing in this software itself. Like in this preprocessor, first of all, once we'll click on this, preferences. In preferences, once you double click in preference, we will get a window which is look like this. So here we need to decide what types of analysis we need to do. So here we are going to do structural analysis and thermal analysis. So these two analysis we need to select. So these two analysis I am just showing in next slide. You can see here I have select. That means I have ticked this two structural analysis two part. So now what happens? We will start our analysis. So in this preferences, generally we need to do these things. After that, the second step is called, what is called? Preprocessor. So in this preprocessor, you can say, here generally we need to decide what types of element we need to use for doing any types of analysis. What is the unit system generally we need to use there. After that, we need to specify what should be the material property. And here also we need to do the modeling part. And finally, we need to do meshing part. Meshing part means discretization part. That means here dividing the structure into finite number of elements. How it is, one by one I will show. So here you see in you can see in preprocessor, first of all, what we need to do, we need to click on preprocessor. You see, then what happens? A set of window will come. This is the subset of this preprocessor. So here, so many different operation we can do. So in preprocessor, the first step is element type. So in this element types, once you click add, edit, delete this button, so we can get by using this. Generally, we need to select our type of element. Like here, we first select add, edit, delete by using these things by clicking add element. Once we click add element, you see here we are choosing this thermal mass element. So in this thermal mass element, you can see we are doing three-dimensional analysis, which is required a solid element. So that solid element also I'll choose, which is a three-dimensional analysis. Then there will come different types of thermal mass model or thermal mass element. So I have already told you here generally for doing tangent thermal analysis, solid 70 element is most appropriate. So that's why what happens here, we decided this solid 70 element that you can observe. Okay. That you can observe. So solid 70 element I have already decided here. So after that, once we click OK, then it will add. Okay, and it will show in left side. Okay. After that, we need to incorporate what? What is the temperature unit? Here we can decide. If we click temperature unit, a window will appear like this. So in this window, there will be generally by default, there will be Kelvin. So there generally, if we click in this right side button here, generally there a set of different unit will come that we need to decide. So here I select Celsius. Whatever the things I will select, that according to that generally our outcome will come. Okay, this you should keep it in mind. So after temperature unit, now we need to define our what it's called material property. So next menu you can say, so first two menu I did the work, you can observe. Now we need to apply the material property. So here you can see, here I have shown you that how to put the material property here. So for putting material property here, you can see you need to select material model, click on material model. Then in this material property, you need to select this material model. If you click material model, a window will come which is similar to this. So here generally we need to add, you see, conductivity, specific density. So in right side generally, if we click on conductivity, so a window will come. So there generally by using this add temperature button, we can generate different set of column. Like here you see, by clicking on add temperature in 5 times, then 5 number of, you can say, column will come. So where at T1 equal to let 0 degree centigrade, what should be its thermal conductivity? Kx means thermal conductivity. At T2 degree centigrade, what is the thermal conductivity? T3, what is thermal conductivity? T4, what is thermal conductivity? Everything we need to specify here. After that, generally, we need to just whatever the data required for doing thermomechanical analysis, that related data once we'll put, you see that will add in left side of this, you can say window. That you can say first, like you see, this is thermal conductivity, this is what it's called density, then a specific heat. These are the things also will generally add like this way. Then what happens? From right side button, if we add this thing, automatically this data will stored. Okay. So after that, we need to do the modeling part. So for doing modeling part, you see the next step we need to select, that is called modeling. So this modeling window that you can observe very clearly here. So in this modeling window, generally you can generate your model. So here you can generate the model from the scratch in the sense by creating the key point, like key point 1, key point 2, 3, 4. By using this key point, generally you need to draw the line. After that, drawing the line, by using the line, you need to generate the area. And after the area, how to generate a volume, that step by step just I am showing. So first of all, we have specified the key point. This key point generally how to specify, that you can see, that is create key points. It's given in active coordinates. Active CS means coordinate system. So there we need to specify this X, Y, Z. Here you can see this X is let 0, Y is 0.1. Okay, like this we need to specify the thing. So, and this key point number, generally depending upon the number, you need to change the key point number. If this key point number you will not change, then what happens? It will create problem. This you should keep it in mind. Problem in the sense, like if the key point number is same, in same point, there will be generally this next key point will be overlapping. This you should keep it in mind. So that's why whatever the key point will specify, every time this key point numbering you need to change, like 1, first case 1, second case 2, third case 3, fourth key point 4, that you need to specify. After that, okay, I need to create the line. For creating line, you see first key point, then line is there. So that this line 1, 2, 2, this 1 line, 2 line, 3 line, and 4 line. By this key point, generally we generate this line. After that, by this line, we can generate the area. The second step is there. So by this, generally we can generate the area by selecting this 4 line. This is a square area you got. After that, let us consider we need to what is called provide the thickness there. For providing the thickness, here generally what are the operation we need to do? That is called, generally after create, we need to go to operate menu. In this operate menu, there is an option that is called extrude. This extrusion we can do. Extrusion means let us consider we want to provide some thickness on this area. That things generally we need to specify there. So by using that thing, generally we need to create this volume. By this creating this volume, generally this is, let us consider one volume, this is another volume, this is another volume. By this way, generally we create this 3 volume. So in this 3 volume, generally this 3 volume, let us consider this middle zone is what is called welding zone, and this 2 side is generally what is called plate surface zone. So in this middle zone, generally heat source model will move. So after modeling, we need to what is called mesh it. For doing meshing, generally it is better to use fine mesh near the weld zone and coarse mesh away from the weld zone. So how to do fine mesh and coarse mesh, that related things already mentioned in this what it's called window itself. What I'm telling here, you can see this line here. I have dividing at weld zone. Generally, it is a small division, and at away from the weld zone, far away from the weld zone, it is very bigger division. That you can observe. So wherever we are going to apply the heat, there generally what happens, that means where the moving heat source will be there the will make fine meshing. Fine meshing means there will be a small element, and away from the what is called weld zone, will make gradually coarse meshing zone. This you should keep it in mind. So that way, generally we divide this division, and after that, next slide I am showing just what it's called, how the division is look like. That you can observe. So here you see, this is the center zone is welding zone. So here you can see this fine elements we created. Away from the weld zone, I created a coarse mesh zone. What I am telling, understand? That you can observe. After that, generally meshing, we need to specify what is called boundary condition, and what is called, we need to specify the moving heat source in that model. How to specify those things, that I am going to now represent. So let us consider in solution. After that, after preposition, now we need to go to solution menu. So in this solution menu, there again, if we click on solution menu, there will come lot of sub-step of this solution menu. So here generally we can decide our type of analysis. We can decide our what it's called moving heat source model. So this related boundary condition, different thing, time stepping, different thing generally we can specify here. So how we can specify here, that thing generally here it is provided. So for solution, here you can see once you click on analysis type, what types of analysis we are going to do. There we need to decide generally new analysis. If we click on new analysis, one window will come. So here you can see for thermal analysis, there we can do steady state thermal analysis, transient thermal analysis, and you can say another one is called substructuring types of analysis, that also we can do. So here generally our analysis type is transient thermal analysis. That's why I select transient, which is a time dependent phenomena, that you can observe. Once you select it, that generally you can say a black dot will appear. After that, we need to specify the boundary condition. So here for apply, you see, after this what is called type of analysis, we need to apply the boundary condition. So in apply menu, there you see there are convection menu. Here you can see there is this convection menu, there is radiation menu. So this convection menu generally the apply thermal convection. Here you see this convection we need to put on the surface area which is generally connected with what it's called, which has a contact with atmosphere. So there will be a heat loss due to convection. That related thing we need to specify. So by clicking all the menu like thermal, then convection, if we'll go, then in convection on area, once we'll select that area, we need to select like all the outer area of this plate. Generally, we need to specify boundary condition of, that is convection boundary condition. How to specify that I am just showing. So once we click this on area, a window, a arrow will come. By this arrow, generally we need to select different area. So by this, generally what it's called, we need to specify the what is convection. In this convection, generally we need to define what is the convection coefficient value. This convection coefficient value can be constant convection coefficient value, or this convection coefficient can be what is called temperature dependent convection coefficient also. That we need to specify there. Okay. Now after that, radiation generally we need to put. So in this apply menu itself, it is there. So apply radiation. By applying radiation, we can apply the radiation boundary condition also here. Now we will apply load. So how to apply load? You see, for that thing generally here I am showing. This you will get very nicely. So here you can see. So apply. After that, okay, let's here we are interested to do what is called heat source model starting from this left side. From left side, generally what happens? Here generally we can write what it's called APDL code. APDL means ANSYS parametric language code actually. Parametric design developing language code. By using this FEDL code, generally we can develop code by this generally, which is generally a, here it is a moving heat source. Here generally heat source will move. I have already shown you how the moving heat source is defined for volumetric heat source, for what is called surface heat flux model. That related things already I have discussed in the lecture. So accordingly, generally here we need to write a code. That code generally we need to specify here by using this APDL. Then automatically generally here this subroutine will do the thermal loading part. So that thermal loading, after thermal loading, generally here we need to solve this. We need to solve this, what it's called, load cycle. So how to solve this load cycle? In this solve menu itself, you see, in this solution, there is a menu that is called solve menu. In this solve menu, generally, there are three options are there. You can see one is called current load step. Another one is called from load step file. Another one is called adaptive mesh approach. What I'm telling, understand? So here generally in transient thermal analysis, there can be a number of load step. Okay, that load step, let us consider here the load step is varying from 1 to 100. So all the load step generally we need to solve. So 1 to 100 I select and its increment is 1. After that, once we click OK, so 1 to 100 number of load step it will solve. So once we start this, then what happens? A window will come, all the solution will be completed. Then what happens? These types of alarming window will appear, that is called solution is done. After that, we need to close it. So after closing this window, generally we need to go for getting the what is called pictorial view of thermal history, how it's look like. That things we can get. That means control plotted related things we can get by using this general post processor menu. So in general post processor menu, you see generally depending upon the time step type, generally at a particular time, what should be the what is called temperature distribution over the entire plate, that we can see. Like what happens, the let's start the general post processor. We want to see at a particular time. Let us consider at a time of let us consider 15 seconds. How the temperature is looks like, that I'm going to see. Okay, or you can say 15.1 second, how the time is look like, that I am to see. So by peak, a window will come which is showing this load set versus time data. So if we just select any one of this load set data, after that if we just read that data, at that time step, how the temperature control is look like, that you can see. During that times, how the moving heat source is look like, that you can observe from there. Now, to simulate the weld deposition in this model, here we used a technique that is called element birth and death techniques. What is element birth and death techniques? Here you can see generally here the gradually we are depositing the material. So from here to here, this much of things we did the deposition, and this much of things is already there is a gap. What I'm telling, understand? So what we used to do by using element death and birth technique, generally first of all, we develop the entire weld bit geometry, and we generally measure those weld bit geometry also. After that, generally we need to select those weld bit geometry. After selecting this weld bit geometry, first of all, we need to deactivate all these element in this weld zone, where generally these types of gap will create. That means deactivate means we are killing the elements. That's why it is called element death and birth technique. So first of all, we are deactivating the element on this weld zone. Then it will create a root gap. After that, generally we gradually activate the small portion of the weld bit, where generally we use the thermal load, or you can say load data. That means weld bit load data. After that, generally that means for applying this weld thermal load, first of all we need to activate that portion where we are applying this weld temperature data. So once we apply, first of all, that for that generally what we need to do, we need to activate that element. After activating the element, we need to apply the temperature, or you can say volumetric heat source. After that, then generally next part we need to activate. This way, generally a small part we need to activate, and what it's called, we need to apply the load. So wherever the activation will be done, there we need to apply the load. In this way, we are doing element what is called death and birth technique. So first of all, creating root gap. Generally, we need to kill all the element on this zone. After that, gradually a small portion we need to activate, and there we need to apply the heat source data. That means heat source data means volumetric heat input we need to apply there. So after this way, generally once we do the things, we can mimic the well bit deposition part. Okay, so that I am just showing. Just after that, we want to see what is the temperature data at a particular time, or what is the temperature data over a particular time. How to get that data, that related thing generally now I am showing. That thing generally we can observe by using this time history post-processor menu. So in this time history post-processor menu, here once we click time history post-processor menu, a window will appear which is look like this. So in this window, generally here this greens button represent generally add data menu. Okay, so if we click on this green data, another window will come. Here generally let us consider we want to see the what is the nodal temperature data. So if we click on nodal temperature, a arrow will come. Based on this arrow, we need to select any node. So let us consider we want to see at 12 center line node. At that 12 center line, how the temperature distribution over the time, that want to see. So let us consider any further location we want to see how the temperature data. That thing generally we can get by using this window. This you should, or this menu. This you should keep it in mind. After that, this thing generally we can store. We can extract this data as per our desired location in the form of what is called CSV, that is comma separated value, what is called, or which is in Excel form. Okay, that is in Excel file. So after that, generally we need to go for structural analysis. So this way generally we need to do the thermal analysis, and after that generally we need to do the structural analysis. So in a structural analysis, generally this thermal load data, generally you can say we import as a load value, that due to this thermal load data means temperature history data over the entire plate. Once we will import in the structural analysis, that temperature effect generally is solved with the help of this structural analysis. Due to this temperature history or temperature data over the entire time of this welding, whatever the structural changes will occur, that will create some deformation, that will create some what is called stress generation. So what should be the stress generation after completion of welding and after cooling the welding? That related thing generally we can estimate by using this structural analysis. So that things also, if required, you can contact with me. I can provide you the detailed PPT is with me. I can provide you the detailed things. Okay. So that's all about this structural thermomechanical analysis for prediction of residual stress distortion and transient thermal history by using commercially available software package ANSYS. Okay. So if you have any other queries, you can ask me. So I am just going to stop sharing the window. So if you have any further queries, you can ask me. There is no further query. So as there is no further query, as well as time is up, so I think we can quit here. Hello, am I audible? Hello. 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 Hussain, do you have any queries? Hello. So shall I quit here? Okay, actually, time is up and no further queries also are there. So shall I stop now? Okay, Kunti. Thank you, sir. I am leaving. Okay. Oh, thank you.